Hello, welcome to the IB2d video tutorials. This is tutorial 3, which will give you the basics about how to construct the immersed boundary geometry, as well as how to format some of the fiber model input files. In particular, this tutorial will pick up right where tutorial 2 had left off. We will examine the input files, including the dot vertex and dot spring files for the oscillating rubber band example. So without further ado, let's revisit that skeleton example that we ran the oscillating rubber band from tutorial 2. If you've deleted the data from that simulation, don't worry. In this tutorial, we will not concern ourselves with data visualization or data analysis. That will be coming in a later tutorial. Don't worry about rerunning yet. Okay, we should all be looking at this same screen. Perhaps yours doesn't have the data spit out from the simulation, but that's a-okay. Now let's just reorient ourselves very quickly from what we talked about in tutorial 2. Tutorial 2 left off basically saying that to actually run a simulation in IB2d, we need to just call the main2d.m file. However, the main2d.m file does not depend on this make your geometry and input files .m file script. The whole purpose of this script is to produce these practice.spring and practice.vertex files. Otherwise, the IB2d code won't consider it at all. .spring and .vertex file are imperative to have for your main2d.m file call. Now recall, the only reason we need a .spring file at all is because we have a designation inside the input2d file that says the IB2d simulation will be looking for a .spring file associated with a spring fiber model. In all simulations, we will always need a .vertex file. So without further ado, let's check out and see what's inside the make your geometry and input files script and explore how it produces those two necessary input files. Okay, let's go ahead and open up that script. So now that we have this file open, let's just scroll down and see what's within it. So if we scroll to the first function, cleverly named make your geometry and input files, we can see what type of variables are being made. The first variables are grid parameters. We want to make sure that these match what's in the input2d file. Namely, we have the resolution of the grid itself given by this nx equals 32. And then we're also told what the length of the actual grid is, or the actual domain. Here it's size 1. That leaves us with the grid spatial resolution of basically just the length divided by the resolution. I would also like to emphasize at this point that by defining these variables, we're just going to be trying to use them to create the Lagrangian geometry. This in no way affects what's in the input2d file. We only care that they're going to be consistent with one another. Now if we scroll down, we can see kind of other variables associated with the Immerse structure geometry. Namely, we're asked what the Lagrangian point spacing is. We want to have the Lagrangian point spacing, or basically the distance between two successive Lagrangian points, to be about twice the resolution of the Eulerian grid. So we want the distance then to be about half the size of the grid resolution of the Eulerian grid. Next, we're just giving a variable name or string name to what we're calling the structure. Here we're just calling it practice. Remember, this is where we had those practice.spring or practice.vertex files. This is just going to be the string that names those. Finally, in this main part of the function, the next thing we have is a call to actually construct the Immerse boundary geometry. Here, this give me Immerse boundary geometry, we're just passing in the Lagrangian spatial resolution, as well as, or more or less, the Eulerian grid points, the number of Eulerian grid points. And this function is just returning two things to us, the x and y coordinates of the Lagrangian points themselves. And then finally, we're just plotting those Lagrangian points below. This, of course, just makes sure that we're actually creating the structure that we want. So let's scroll down and see what else is inside this file. The next couple functions are what actually are going to be printing the input files for us. First, we have this .vertex file that will be printed by print Lagrangian vertices. This function will just print the .vertex file associated with the x and y coordinates of the Lagrangian points that we created before. Next is what we're going to see are all the functions associated with printing the fiber model inputs. In this particular example, we only have springs between each of the Lagrangian points, so we only need a .spring file. You will also notice that for the .spring file, we also need a spring stiffness and to also declare a spring resting length. Each spring could have a unique resting length and stiffness. However, that becomes a bookkeeping nightmare. What's going to be important for this .spring file is basically saying what Lagrangian point is tethered to another Lagrangian point by a spring. So this is going to become a bookkeeping exercise. There'll be more on that later. Now, we won't emphasize it too much in this tutorial, but as you can see, there's other types of functions associated for printing other fiber model inputs. Namely, in this example, we have a .beam and .target file that are both being commented out. All this to say that every fiber model we have, or any time we have a Lagrangian point connected to another Lagrangian point by some type of fiber model, we have to have an associated input file associated alongside. In this particular example, we're only connecting Lagrangian points by springs, so there's not going to be any beam connections or target point connections or porous points or anything else. Now let's jump into the guts of this code and see how we construct the Lagrangian geometry as well as how we print the vertex file and .spring file. Before we do any of that though, let's actually just remind ourselves or take a quick step back and ask ourselves what we're hoping to accomplish in this simulation, just so we all know what the goals are of creating the geometry and what we're trying to do. So let's quickly review at this point. In order to run an actual simulation, you always need a .vertex input file. This .vertex input file will include all the x and y coordinates of the original positions of the Lagrangian mesh. Furthermore, if you want your Lagrangian mesh to have any type of physical meaning or material properties, you will also need to include an input file associated with that specific fiber model. For example, a .spring, a .beam, etc. And all the input file formats for each of these fiber models can be found in the following two papers. Now, once you've created all the input files, you can try running the simulation by calling the main2d script. Now, main2d will look for any input files that are flagged to be there because of what's in the input2d file. The input2d file, remember, is where you declare what fiber models you're expecting to use in your simulation. For example, in this particular input2d file, the only fiber model that's listed to be there is springs because of the 1. All the other fiber models have zeros, illustrating that the simulation isn't going to be used that particular type of model. I would also like to emphasize at this point that the whole purpose of the Make Your Geometry and Input Files script is nothing more than to produce the input files necessary for the simulation before you actually try to run the simulation. IB2d will never call this script when it's actually running a simulation. This is just for the prep work beforehand. Now let's go ahead and quickly motivate what type of geometry and input files we'll need for a rubber band example that we did in tutorial 2. Remember, we started off with an outstretched rubber band and released it in fluid and saw what happens. Next, let's go over what the goals of the simulation are and how we can achieve those goals through different types of fiber models. So let's quickly review what our goals are for this simulation and how we hope to achieve those. We want to start with an outstretched rubber band. In other words, we're going to start off with an ellipse. But mind you, This ellipse has to be composed of individual Lagrangian points. Since we want our Lagrangian mesh to start off in this configuration, in the Make Your Geometry and Input File script, we're going to need to solve for the x and y positions that correspond to this elliptical configuration. Upon doing so, we're also going to be inherently defining a length scale for our simulation. These x and y coordinates are what we're actually going to print in the dot vertex input file. However, since we don't want these points just to sit there in the fluid, we want to have some type of material properties. Since this is an outstretched rubber band, we could imagine tethering each of these Lagrangian points to its neighbor. Upon doing so, we're hoping that once the simulation starts, these springs will cause this entire configuration to oscillate. And eventually it'll oscillate towards its lowest energy state, which just makes it circle. So we know we hope to tether each Lagrangian point to its neighbors by a spring fiber model. However, to actually use any type of fiber models, we have to give a designation or an index to each of the Lagrangian points. Now, the index will essentially just be the order that they're listed in the dot vertex file. So the first point listed in the dot vertex file corresponds to the Lagrangian point with index 1. Then the second point in the dot vertex file corresponds to the Lagrangian point with index 2. The next point with index 3, and so on. Next, we want to actually explicitly say what springs are connecting what Lagrangian points. Now, this is where bookkeeping comes into play. For example, we know that Lagrangian point 1 is tethered to both Lagrangian point 2 and Lagrangian point n in this case. However, we can cleverly choose how we list out these spring connections to make the bookkeeping the simplest. For example, if we have a starting spring index of 1, we can say that the ending spring index would then be 2. However, we don't want to then say that a starting spring index could start with 2 and then end with 1, since we already defined that spring connection. However, it looks like we could take the spring with index 2 and connect it to the spring with index 3, and then 3 to 4, 4 to 5, and we can keep going. And eventually, since this is a closed rubber band, when we land at the nth Lagrangian's point, we will just reconnect that to Lagrangian point 1. The bookkeeping exercise here wasn't too bad. However, you could imagine if you have a much more complicated geometry, with much more complicated spring connections, beam connections, porosity type connections, and so on, that this would become a very non-trivial exercise. So bookkeeping for all these types of fiber models are very, very important. And that about does it for the types of connections that we need to be thinking about to put into our dot spring input file. No matter what type of an immersed boundary simulation you're going to be running, these are the types of things to think about as we're trying to prep the simulation and create all the necessary input files. Let's once again revisit the Make Your Geometry and Input File script, and let's see what's going on. Welcome back to the Make Your Geometry and Input File script. First, we're going to explore and basically see how we can create the elliptical geometry. Remember that ellipse is composed of individual Lagrangian points, so we need to figure out what the x and y coordinates of each of those points are. And if we scroll towards the bottom of this script, we'll find a subfunction called Give Me Immersed Boundary Geometry that will do just that. Now this subfunction isn't too complicated in this particular script, since all we're doing is creating an ellipse. But you can imagine if you have a much more complicated geometry, then just coming up with the geometry or the x and y values for each of the individual Lagrangian points could be quite cumbersome. And unfortunately, many immerse boundary applications require very complicated geometries, so you might be spending a lot of time writing these kind of routines. So now if we explore this function, what we want to return is basically two arrays, one that has all the x values and one that has all the y values for each of those points along that elliptical geometry. To create the ellipse, we just tell it the length of a semi-major axis as well as a length of the minor axes of the ellipse. Now, the part that I want to emphasize a little bit here is, since this is just a practical example and we're not trying to do any research-heavy computation with this, I'm just letting n, or the number of points in that ellipse, to be basically twice the Eulerian grid resolution. And remember, in practical terms here, we're beginning with an outstretched rubber band and modeling oscillations of that rubber band until it becomes a circle. And we're hoping that once it becomes a circle, then the points will be equally spaced, rather than starting off equally spaced in that elliptical configuration. In other applications, though, you might have to put in a lot of effort to create a geometry that has equally spaced points everywhere. This could be very non-trivial. Also, as a rule of thumb in immersed boundary simulations, we'd like the Lagrangian mesh resolution to be about twice that of the Eulerian mesh. Now, to actually get the individual Lagrangian points, we're just going to simply write a for loop that goes over all the number of points we're hoping to have. Remember, twice that of the Eulerian mesh resolution. But then to actually fill these x and y coordinate vectors, we're going to harness everybody's third favorite topic from Calculus 2, polar coordinates. In using polar coordinates, we're just going to easily center an ellipse at the point 1/2, 1/2 to create those arrays. And that'll about do it for creating the geometry in this relatively simple immersed boundary example. At this stage in practice, we really want to make sure that this geometry is giving us back what we think it is. So we should be plotting it as well as testing it to ensure that. But this is a relatively simple case with just an ellipse, so let's just move on. But the fun's not over yet. Now that we have the geometry, we still need to print all those input files that are actually necessary to run an IB2d simulation. So let's check that out next. Okay, so let's just scroll then to where the dot vertex file gets created. So here we're going to print the Lagrangian vertices associated with the x and the y coordinates for that ellipse. Remember here the struct name is just our string variable that we called practice. Let's scroll down to where that dot vertex file gets created. Now, if you're unfamiliar with I/O, or really reading and writing to scripts or to text files, don't worry. Every fiber model in IB2d has a function that will create the necessary input file for that fiber model. They're just all in various examples within the software. And as briefly mentioned before, all those input file formats are found in various different IB2d software release papers. In this particular subfunction for creating these dot vertex files, you'll notice that all we really need to do is print the x and y coordinates of each point in that Lagrangian mesh. And from glancing from this figure from one of those papers, it illustrates the true file format for these dot vertex input files. The first line should include the total number of Lagrangian points, followed by all subsequent lines having the x and y coordinate pairs of each Lagrangian point. And if we were to run the make your geometry and input file script, we would see the practice.vertex file be created containing exactly that inside. That about does it for creating the practice.vertex file. Next, let's turn our sights to how we create that practice.spring file. Okay, so scrolling up, we get to the point where we want to print that dot spring file. Now, as compared to printing the Lagrangian vertex file, this one's a little more complicated. We can also define a spring constant within this file as well as a resting length for each of those springs. And then, of course, we want to actually call the file to print our Lagrangian spring or the practice.spring file. And we can scroll down to where we actually do that. Now within this file, you'll notice that it looks a little more complicated, maybe just slightly, than the .vertex file. These .spring files can be very complicated because, as mentioned before, we could have very complicated spring connections around the entire geometry. Rather than just every single Lagrangian point being tethered to its neighbors, we could have them, if this was still with an ellipse, them going across the ellipse, doing diagonals, and so on and so on. And within this subfunction is where we're going to have to define each and every one of those spring connections. Okay, remember for this example, we're only having spring connections between successive Lagrangian points going around that ellipse. So a Lagrangian point is tethered to its neighbor on its left and its right. To do that, we're just going to use this for loop here. This for loop is going to sweep over every single Lagrangian point and then check to see if it's the nth Lagrangian point so it can reconnect that to the first Lagrangian point. Otherwise, every Lagrangian point will just be tethered to the subsequent Lagrangian point after it. So 1 to 2, 2 to 3, and yada yada yada. Now beyond just saying what Lagrangian point is tethered to what other Lagrangian point, for each spring connection we also have to say what the spring stiffness is and resting length is of that particular spring. And if you so desired, every spring could have a different stiffness or a different resting length, but mind you, that could be tens, hundreds, and probably thousands of extra parameter choices that you'll have to make. And just like all other fiber models, the input file formats can all be seen in those papers I showed you earlier. For example, this is what the official format looks like for a dot spring file. And if you have a really good eye, you might notice there's an extra quantity that we didn't print in this input file below, the degree of nonlinearity. If the degree of nonlinearity isn't in that input file, IB2d assumes a linear spring connection. Otherwise, you can define your nonlinear spring there. Now, if you run the Make Your Geometry an Input File script, you should see this practice.spring file be created. Inside this practice.spring file, you'll see the first line tells you how many total spring connections there are, followed by all subsequent lines telling you what Lagrangian points tethered to another Lagrangian point by a spring, as well as their associated stiffness and resting lengths. And that about wraps it up for this .spring input file. Remember, for this particular simulation, we just needed a .vertex and .spring file. But if your model includes any other type of fiber models, you'll need to include those input files for those as well. And those file formats can be found in those papers I've showed you earlier. On a fun note, all of these input file formats are consistent with the input file formats in Boyce-Griffith's IBAMR package. However, there are some fiber models, as previously discussed, that are in IB2d that are not yet in IBAMR. And this wraps up Tutorial 3, how to construct the Immerse boundary geometry and how to format the fiber model input files for that particular example we ran with the rubber band. The next series of tutorials will concern themselves with data visualization using the open source software Visit, as well as getting into the nitty-gritty of data analysis with the package that's available in IB2d. Thank you for checking out this video, and happy computing.